Okay. So like I was saying, we are playing a game which is governed by the toss of a coin. So game governed by the toss of a coin. Okay. By the toss of a coin. Okay. So anytime, now this is the condition. Anytime a head shows up, okay, anytime a head shows up, you will move one rank. You will move one rank. Okay, good. So meaning you move one level. Good. Now, when a tail shows up, anytime you have a tail, okay, you move to the very bottom. So it means you are going back to the very bottom. Okay. Now there are 5 levels. There are 5 levels in the game. 5 levels in this game. Okay. Now, and as long as or let me put it this way, when you get to the top, okay, and there's a head appears. So at top, let me put it that way. So let me take this off. So at level 5, so at level 5, when a head shows up, okay, when a head shows up, you remain at what? You remain at level 5, okay? You remain at level 5. So I want you to construct the first transition probability for me. Construct the first transition probability, Pij, for me. So I want the matrix, not the model. Okay. So think through and then solve it at your end. Let's think through in a minute or two, and let me have your answers.
So
Yes.
Go through it again so that I will understand. I don't know if my colleagues have understood, no problem. But personally, I need to get understanding of the question you have just
Okay.
posted.
So let me read it again. Let me read it again. We are playing a game, okay, governed by the toss of a coin. Anytime you toss a coin and a head shows up, you move one step, that is one level ahead. When a tail shows up, you move to the very bottom, okay, of the game. There are 5 levels in the game. When you are at level 5 and you toss a coin and it still comes as a head, you will remain at level 5. But if you have a tail, the rule says you come to the very bottom, which is what? 1. And you are supposed to construct the probability, the first transition probability for such a game or for such a movement. So think through it, solve it at your end, and then give me your feedback. Yeah, I'm sure we've done 2 minutes now. Anybody with an idea? Anyone with a solution?
Not yet.
Okay, this solution comes with 1 mark. Okay, I guess I'll have to take back my 1 mark. Or somebody has a solution. Yusuf,
Hello, sir.
do you have solution? Gabriel is, yeah, Gabriel.
Yes, sir. Please, I'd like to know the solution that you are expecting for us to bring. Should we bring it in the probability or in the structure? That's the levels.
In the probability, in the matrix form.
Okay, sir.
Mhm.
So from probability I to J.
Okay. Will be equal to
Is
what?
equal the level starting from 0 to 4.
Okay. 1. Okay, so you took it 0 to 4. Let's make
Yes,
it,
sir.
because I said maximum level is 5. Let's make it 1 to 5.
Oh, okay, sir. Sorry, 1 to 5.
So 1, 2, 3, 4, 5. Then we have 1, 2. That will be too small. 1, 2, 3, 4, and 5. Okay, what next?
Chat 1 1 from 1 1. We have the header.
We have what?
That's the head.
Okay, you want me to use
Head. So the head and tail.
No, not at all. The secret which I did not give to you is when I say it's governed by the toss of a coin, what do I mean? Anytime you toss a coin, what is
Either 1 or 0.
what's the probability of observing a head?
It's 1 over 2.
Yes, 1 over 2. So the
Yes,
probability is what I didn't give you. I intentionally didn't give it to you. So when you have a head, the rule says if you are in state 1 and you get a head, you move to what? State 2. But the question is with what probability? The probability of obtaining a head, which is 0.5. Okay, that is what I mean by governed by the toss of a coin. And then,
okay,
yes, and if you get a tail, you remain in what? State 1, because it's the bottom. So that will be 0.
So your questions are loaded with so many calculations.
Yeah, so you should be able to, Then from state 1, there is no way you can get to state 3, because the rule says if you get ahead, you move only 1 rank. So you can't move 1 to 3. That would be 0, 0, 0.
0.
Then if you are in state 2,
Moreover, it will be equal to 1.
Yes. If you are in state 2, if you get ahead, then you will not stay in state 2, you move to state 3. So that will be with a probability of 0.5. And if you get a tail means you have to drop to level 1, because that is the rule. Anytime you get a tail, you are dropping to the bottom, or more or less game over. Okay, so you go back to state 1, which is with a probability of 0.5. Then this will be 0, 0, 0. If we are in state 3 and you clock ahead,
So you are beginning again.
Yeah, you go to state 4, 0.5.
4.
If you get a tail, yes, if you get a tail, you are going back to state 1, 0.5.
Bottom.
Then you get 0, 0,
0, 0, 0.
If you are in state 4 and you get a tail, you come to 1. If you get a head, you go to 5. The rest will be what? 0, 0, and a 0.
0, 0, 0.
Good. If you are in state 5 and you get a tail, you come to 0.5. If you get ahead, yes, if you get ahead, you remain in 5. The rest will be,
you remain at 5.
Yes, 0, 0, 0. So this is the transition probability matrix for such a game, a computer world game. Yeah, that's quite exciting, right? So you can easily model this. So you can easily model a computer game based on this. Okay. So now let's try constructing the Markov model. Okay, for this process. It's going to be an exciting one. So we have state 0, state 1, state 2. Let's put state 3 here. No, let me put state 3 somewhere here. So I have state 3, state 4, and state 5. Now, probability, oh, okay, we don't have a state 0. We only have state 1. So we have probability of moving from, there's a possibility of moving from state 1 back to state 1, which will be 0.5. There's a possibility of moving from state 1 to state 2, which will be 0.5. There is no probability of transiting from state 1 to 3, 4, and 5. So we move to state 2. There is a probability of moving toward state 1 with 0.5. There is a probability of moving to state 3 with 0.5. There is a probability of moving from, no probability of moving from 2 to any other states. Then from 3, you can go to state 4, and then you can also go to state 1 with 0.5 each. Then from state 4, you can go to state 5, 0.5. And then you can also go to state 1, 0.5. Then finally we have 5. You can go to 1, 0.5. And then you can also remain in the state 1. Okay, so we can basically see that regardless of the state you are in, there is a 0.5 chance for you to return back to what? State 1. The probability is quite high for you to always end your game at any point in time. I hope you understand. Okay. So now we want to move on to another exciting rule. Okay, we are going to look at a very exciting rule. Okay, let me clear the screen first. So what rule are we talking about? So if we said Markov chain based on what is happening today, we can forecast what is going to happen tomorrow. We can also forecast what is going to happen tomorrow next, etc. Okay, we can keep going and going and going and going. Now, if we are in, say, a state S, today we are in a sunny day, and there are more than one possible states, okay, which we can move into tomorrow. So let's say we have state S and we have state R, and we want to forecast this is at a state, let's put it T plus 1, and then at state T plus 2, let me make it X at the state time T plus 2. We want to end up in a rainy day. Okay, how do we get the probability of moving from a sunny day today to a rainy day in 2 time steps? Okay, now per probability, rules for probability distribution. If you want the probability of moving from what, let's say A2 and let me make this one A1, the probability of A1 and what, and A2, okay, A1 and A2 will always result in what? P of A1 times P of A2 times P of A2, okay? When the events are independent because here our occurrences are happening over a non-overlapping what? Interval. So they are all occurring at different periods. So they are independent, which means if you want the probability of moving from a state, so technically, let me say trivially, this is how we write it, okay? From T to X, moving from T to another, this thing at another state R at T plus what? 2, okay? This is what I mean. But if you want a probability, more technically, we write T at the probability of X at T plus what? 2 equals to what? A particular state, which is what? R, given that we started X at T was equals to what? S. Okay. How do you get this probability? Now, what we are saying is, because there were 2 possibilities at T plus 1, okay, before you come to R, okay, there is a rule that governs this estimation. There is a rule that governs the estimation, and this rule is based on our basic knowledge in probability distribution, which says that if you are moving, if you want the probability of moving from st to st plus 1 and from st plus 1 to st plus 2 is going to be the probability of what? Okay, x, that will be a1. Let me put it in terms of event, a1 times the probability of what? A2. Okay. However, because there are more than one possible states, okay, which means that we'll be moving from p at s, let's say state 1 was s, to another s, and then from that s to r, and we also have the possible state, which is what? S to r and r to what? R. Okay. Then that rule says that if you want that probability of transiting, regardless of the number of states, is going to be the summation of all the joint probabilities. Okay, from, so now we are going to break, I'm using this example to demonstrate it. So that will be from xt, okay, xt plus 1, okay, given that we came from xt times, that is this portion, so probability of getting to st plus 1, given that we are from xt, times the probability of what? So now st plus 2, the probability of the process at st plus 2, okay, given that we are coming from xt plus 1, okay, st plus 1. Aha. So we call, this is just a simple form of the theory which we refer to as the Komograph Chapman equation. Okay, it is referred to as the Komograph Chapman equation, and it's just a simplified form of the equation. So let's go to the theory and then see what it actually states. Okay. Yeah. So this is what Komograph Chapman equation is saying, that if we are moving from a state at k, okay, to a state at k plus n, and we move through another state time u, okay, another state time u, and there are a number of possibilities in u, right? Then to obtain your probability of transition from the time k to k plus n, okay, the general formula is going to be, okay, let me clear the screen. So the general formula for obtaining that is just going to be the summation, okay, of the probability from k to u. So we start at k, we move through u, and then we are ending at k plus what? N. Okay, so the probability of transiting from what? A certain state I to r in what? From k, from within time interval k to u, times the probability of transition from r to j, okay, from the state u to what? K plus what? T. Okay, and then more formally, like we saw earlier. So that will be probability that the process will be in the future state k plus n is equals to j, given that in the intermediate step x at u was r, times the probability that the process in the intermediate state r, given that the state in the initial time was equal to what? I. Okay, that will give us the probability of transition when we have a number of possible states in the intermediate step. Okay, good. Which is a very relevant, okay, a very relevant theorem which helps us to further estimate the probability of transition, not just for the first step, but it also tells us we can move a step further. Okay, so anytime we are transiting within 2 time steps or 3 time steps, this Komograph Chapman can help us to estimate what? The total probability of moving from one state to the other in n time steps. Okay, so I think let me play the video at this point. Let the video also do its talking a little, and then we continue. I just said, good. And we said that we demonstrated that using this example in class. Okay, how the Chapman Komograph theory, okay, operates. Okay, then once we demonstrated this, we can clearly see that moving from a sunny day, okay, I'm on the last but one step, moving from a sunny to a rainy day, assuming that day one, we are day one on sunny, and we are moving on day 3, means from day 1 to day 2, and then from day 2 to what? Day 3. So it's the probability of moving from a sunny to a sunny day on day 2 times a sunny from the sunny day on day 2 to a rainy day on day 3. So all will become addition. So all probability of transiting from a sunny day to a rainy day, and then transiting from a rainy day on day 2 back to what? A rainy day. Okay, that will give us the total probability of transiting from a sunny day to a rainy day. Good. And to further demonstrate this, we said that this Chapman Komograph theory, okay, helps us to get a general, let's say, equation or a general process of analyzing or predicting future events, which we call as the M-step transition probability matrix. And we demonstrated that, okay, using an example. We said that if you have Pij, you want the probability of moving from maybe a sunny day to a rainy day in 2 time steps. It is just represented as the probability of moving from a state I to J, okay? Then the 2 time steps is the raised to power. And that is just calculated by multiplying the initial transition probability by itself. Means you just multiply the transition matrix twice. Okay? And if you're trying to model the transition in 3 time steps, it is just multiplying the transition matrix 3 times. Okay, which means that if you want the transition probability in the M step, it is just multiplying the initial transition probability matrix by n times. N times is